Right, this video is about development of digital twin. Obviously, we pitch our discussion at the business and application level. Now, digital twin can be developed for different types of systems or different parts of a product. So, for example, it can represent a certain part of a particular product. It can be an entire product itself. It can be powering a process, right, that organization follows. It can be simulating or parallel monitoring the entire system. So either one of these four can be a digital twin application. There are also 5 dimensions that we should be aware of when developing digital twin application. The first one is definitely there should exist a physical system. Now, that's not to say that the digital twin system or the virtual equivalent has to be developed after the physical system. No, not necessarily. But you have to assume that there is a physical system in existence or will be in existence and running in parallel with the digital systems in normal circumstances. Second, there's a model that we need to encode into the software, and that's the virtual part of the digital twin software. And that model can be 2 types. First one is a very specific model that is designed to study a particular phenomenon or to solve a particular problem. We call that a surrogate model. The second one is a more comprehensive model which simulates or incorporates the use of data in a much wider sense. You know, the environment, the processes, and the operations, the costs involved, and etc. Okay, and that we call it a complex model. The third dimension is data. Obviously, there are lots and lots of data that needs to feed into the digital twin system, both the running data of the physical system as well as data from external sources that also feed into the physical as also the virtual system. Fourth are the connections. Well, you can imagine there are lots and lots of connections among the physical system. Equally, there are lots and lots of digital connections among the virtual systems, and there are also connections between the physical system or components of the physical system with components of the virtual system as well. The fifth and final dimension are the services, in other words, the functions, the features, the operations that we're going to provide in a digital twin system. What sort of queries we're going to support, what sort of reports and visualizations it's going to generate to help us with the understanding and problem solving and more. So these are to do with the services to be provided by the digital twin system. So every digital twin system, when coming to design and deploying such side of systems, we have to think about these 5 dimensions and have to get into the nitty-gritty and be able to provide the necessary structure to enable that to happen. What are the values to an engineer, assuming that we have successfully developed and deployed a digital twin system? Well, there are multiple very exciting benefits indeed. Firstly, it enhances visibility across the entire system, visibility across different facets of a particular part or a particular product. It enables the engineer or the assigned professionals to have a full-time monitoring and execution status over the entire system, and it's happening in real time. Enables, of course, the physical system to be simulated in various conditions. And it also allows lots and lots of data to be accumulated as well as being analyzed. And such analysis often lead to good predictions, and that will help the future maintenance as well as fault prevention or prediction or potential fault predictions with the physical system. Obviously, with all this data and the learnings that's derived from it, we can benefit from better design to better design and also to improve an existing product as well as the process. A big benefit of digital twin is a lot of these experimentations, if carried out in the physical world, it may not be possible because of cost, because of risky or dangerous conditions or some extreme conditions which in the physical environment rarely exist or very, very difficult to expect that to happen. And of course, we often use digital twin system to calibrate and optimize initial parameters with the physical system, so that hopefully, it started with a good cause and continuing a good cause. And as we mentioned earlier, predictions can benefit us in several ways, especially if it is kind of critical business systems or life-threatening or crisis management type of systems where, a lot is at stake. So, if I can abstract to the next level, these benefits translate into three main aspects. Firstly is enhance user engagement and accuracy, to helping us to have a more holistic view of the current situations and hopefully making better and sharper decisions. Okay, and secondly, with good use of digital twins, it should help to reduce costs, enhance productivity, which means that it takes faster time to enable something from the design phase to the market, reduce time to market, in other words. And thirdly, associated with the second point, if all goes well, then we should also expect we get more mileage for our dollar. So in other words, reduce risk and also cost. So steps to build a digital twin. Here are the five, very logical steps. First one is identify the values to be delivered by this digital twin, like what we were talking about previously about the services that you want this digital twin to study. Is that a particular specific problem that you want to study, or you want to, monitor, simulate, and discover, rectify problems together with a complete system? So that would be the complex model that you have to develop. So what are some of the insights that you want to gain as a result of deploying this digital twin system? Because that would determine, how detailed you need to represent the digital twin system, the virtual system in particular, because you need to, create, the equivalent of the domain, of the domain rules, the constraints, the values, the necessary data into the virtual system, so that you can, mimic behavior as much as possible as the physical system. And with that, while you're implementing, you have to have in-depth understanding about the relationship, the constraints, as well as the processes involved, among other things, that govern the running of the physical system. And that is usually very tedious and quite substantial in effort. And finally, to put all this together, you would have to build a model using the digital twin software and abide by the constraints, the standards, and whatever rules that it supports you in authoring those connections among the systems, and also lining up the data sets to be analyzed in real time, and also at other times for proper analysis and also for predictions. So these are the 5 steps, basically easily understood 5 steps, but obviously at a very high level. If you are actually doing a digital twin application, you will have to take it down into a lot more details in order to fully operationalize these things. Well, you must be asking, with digital twins, a history of about 12 to 13 years up to now, is it as mature as having, international standards that guide the development of these kind of systems? Well, I love to, but I have to say that this stage, based on our searching and research, we have only found one framework in the manufacturing. There is in existence one framework, ISO 23247, digital twin manufacturing framework, and that framework is designed to help and build maintaining digital twin applications in the manufacturing area, and it has 4 parts. One is overview and general principles describing about what are digital twin and what are the components that you need to set up. And secondly is the reference architecture, a set of documents that govern about the various components and aspects that you need to pay attention to, and you need to follow those prescriptive guidelines in order to set up your digital twin applications. Third one is digital representation of the physical manufacturing elements, and also the last one is also guidelines on how to provide the information exchanges among the various types of systems, especially between the physical and the virtual systems. So it 4 sorts of any compulsory and universal standards that one have to follow. But nevertheless, if history is a guide, in the next 5-10 years or more, we should expect more universally accepted digital twin applications to be developed and adopted. Well, when it comes to different types of digital twin systems, there are several terminologies which are now commonly accepted. First one is DTP, which is digital twin prototype. And as the name specifies, it's more like a pilot system that help us to better design, analyze, observe the constraints, and also the processes that are needed in order to build the physical product. So you haven't got a digital twin yet, you have a pilot system in place or in the pipeline. The second one is DTI, digital twin instance, and that is an instantiation, an instance, a version of the actual execution of the digital twin systems, a digital record of all the things involved when this digital twin system is running in execution. Third one, which basically is built on the second concept, which is the DTA, digital twin aggregate. And with the word aggregate, that means that packing together, the instances. So therefore, we interpret that as a collection of all the DTIs for the same product, and that allow us to query, perform prognosis, diagnostic, and also learning, with regard to the performance, the past performance of our digital twin system. That is indeed a very useful repository of data and set of tools that helps to identify problems and also predict various types of forthcoming potential situations. And the fourth one is adaptive digital twin, and that's really referring to a live digital twin system that you can tweak to make sure that it runs as closely as possible with the physical system, but at the same time can also identify differences and then help us to ascertain whether these differences are acceptable or we need to fine-tune the physical system. And the fifth is a further step from the fourth one, which is intelligent digital twin. And this time we're talking about not only live, but these digital twin actually learn on an ongoing basis. So they can be, self-improving or at least gradually improving in their diagnosis and also in their recommendations, because they learn from past scenarios and be able to come up with better and better judgments as time progresses. So that's a table which helps us to better orient some of the concepts we just covered. So for example, if for this first column that I have bracket, then we are talking about, not a common situation, but there are situations where a digital twin virtual systems exist without a physical equivalent, or the physical equivalent is not yet built or being destroyed or whatever, right? In that case, we have three types of systems that are possible: a prototype, a pre-digital twin, or a digital twin system model, which I'll come back to this later on for better differentiation. In the second group is possibly a large group, and possibly the largest group out of the three is there is a physical system in place, right? And we have digital twin virtual systems running. And we further differentiate into three types. One is simple, little amount of data and fairly straightforward algorithm. Second one is moderate complex of data and reasonable algorithm with complexity. And third one is complex and a lot of data and complex algorithms. All right. So with regard to these three, if you are talking about a prototype, then irrespective of the voluminous and the complexity of the algorithm, then we refer this as digital twin instance, because that's a running instantiation of the digital twin physical system. So if it is using a small amount of data and simple straightforward algorithm, we just call it a digital twin. If the system is having a moderate amount of data and reasonably a sophisticated algorithm, then we call it an adaptive digital twin, as we mentioned earlier. This system not only live, but it can learn as well. And also, same thing for even more sophisticated and complex systems and algorithms. Then we are referring them as intelligent digital twin. And for a digital twin system that has got multiple instantiations of the physical systems, we call them, as we mentioned in the previous slide, digital twin aggregate, right? DTA, because they have many instantiations already and they have accumulated lots and lots of useful data for analysis and learning purposes. So coming back to this table in a horizontal way, we're talking about a system without physical equivalent. We call it digital twin prototype. System with one physical equivalent, a DT, would be a digital twin instance. Then for a pre-digital twin system, which would have no physical equivalent, but for a ordinary digital twin which have a wide range of data, volume of data, and also complexity in the algorithm, then we nicely separate it into calling them digital twin, adaptive digital twin, and also intelligent digital twin. And finally, there are also digital twin that exist, but it's merely generated based on a digital thread, which is a combination or a collation of all the digital records representing all instances of the digital twin execution status. And there is a model that governs the format of these records, and it's called the digital system model. And the actual instantiation of the digital twin is called a digital thread in this case.